Hi, I'm Ricky Su from Xilinx Software and AI Technical Marketing. In this session, we will discuss the Vitis platform methodology. The discussion and demonstration will be based on Vitis 2021.1. The general ideas introduced in this session can apply to all Vitis versions. There are many things we can discuss for platform. In this session, I will mainly focus on the high-level side. Why platform can be beneficial and what's the architecture of a Vitis platform. After the introduction about platform creation steps, I'll give a demonstration. If you have already understood the Vitis platforms, this session will also give you an update of the Vitis 2021.1 new features. You may know that FPGA is good at application acceleration. Traditionally, FPGA development requires hardware knowledge and HDL language. Nowadays, while FPGA is used more and more widely, Xilinx wishes to enable all developers build applications on FPGA, SoC, and ACAP. Besides, it's common that several products in one product line have similar functions but different form factors. It would be best if the developed application could be deployed to different platforms so that we can reuse the algorithm and implementation at the maximum level. These are the targets of Vitis. It enables all developers to build and deploy on all platforms. How can Vitis achieve this target? It defines a hierarchical software platform. To enable all developers, Vitis provides acceleration libraries and domain-specific development environments, such as TensorFlow integration for machine learning, FFmpeg for video. Application developers can work in these environments and think less about low-level implementation. These development environments define a series of acceleration operations and will run the acceleration automatically. Vitis allows users to develop acceleration kernels with RTL and C language, so the hardware engineers who know RTL and the software engineers who use C and C++ can both work with their preferred languages. To enhance the reusability and portability of the applications, a software layer, Xilinx runtime, and a layer of Vitis target platform connect between user programming interface and the deployment targets. XRT provides a unified software interface for high-level applications, so that the control in high-level applications are transparent to hardware. The platform can translate the commands to different deployment targets according to the hardware features. For example, the DDR controller implemented by MIG IP and by MPSoC PS DDR controller has the same hardware interface. Acceleration applications can adapt to these two platforms with no code modification. The embedded platform and the data center platform have a unified architecture, so one application for one platform is easy to port to another. Here is an example of the platform. For all Alveo cards, PCIe interface IP core and the DMA is in the platform. The acceleration kernels can be switched for different applications. In one case, the kernel can be a gzip algorithm accelerator. In another case, the kernel can run authentication algorithm acceleration. The platform can serve these two kernels well because these kernels only require the fundamental platform features like PCIe channel for data transfer and local DDR memory access for data storage. Platforms can support different applications. Acceleration kernels can be applied to different platforms like U200, U250 with no code change. Embedded platforms like ZCU102 base platform can also work well. The universality of platform and kernel is one advantage of Vitis Flow. Let's look at another example of a custom embedded platform. Suppose you designed a board with a MIPI interface for camera input. In that case, you can provide a platform with MIPI video IP core. Application developers can use it for different applications. For example, it can work for video encoding. It can also work for video analytics. The analytics can be different based on the algorithm. Object detection, object recognition, with or without machine learning. Similarly, the application developers can easily port their applications and acceleration kernels to other platforms with the same interface. For example, when the board updated the DDR capacity, it only needs to rerun the implementation after updating the platform. The application code doesn't need to change. From the examples above, you may conclude an idea for platform creation common rules. In general, the platforms provide the facilities to kernels in standard XE interfaces. Except general facilities like clock, reset, and interrupt signals, they mostly translate the external I/O interface, especially the data channel, to memory mapped XE interface or XE stream interface. If the I/O interface should be controlled by processors, it doesn't need to export to kernels. The traditional FPGA development flow is very flexible. Users can do anything with HDL. Flexibility is a double-edged sword. It reduces the reusability and leads to a longer development phase. The Vitis platform-based design methodology sacrifices some flexibility because application developers can only use XE interface, but it improved ease of use. This change will also bring benefits to the ecosystem. With traditional Vivado flow, it's a common problem that the components are not in a standard interface for logic or standard API for software. Interconnecting multiple IP modules with different interfaces could be time-consuming if they were not originally designed to be connected. Besides, the tests for these IPs are usually under a specific context. When the context changes, it needs additional efforts to verify and fix bugs. To make components more reusable, Xilinx has adopted the XE interface for a long time. Most of Xilinx IP now has XE interfaces. It makes the connectivity of IP extremely easy. Once we standardize the interfaces, the ecosystem evolves naturally. Since the XE interfaces are standard, you will wish to use one line to describe the connection of two XE interfaces with around 30 signals. V++ in Vitis can help you do that. You will wish to isolate the reusable parts and the unique features of a design. That's the platform feature architecture. Higher level abstraction naturally happened. What the impact on users? The reusable part they develop will become isolated and portable. It's easier to validate because the logic and the software interfaces are all standardized. Once it's validated on one platform, it should run on all platforms. Since the data flow is standardized, Xilinx can create more advanced tools for common requirements. For example, XRT can generate profiling data, and Vitis Analyzer can visualize data transfers. Traditional flow can't do this, because every developer has his unique control pattern. Now you know the benefits of a Vitis platform. Let's dive into the platform architecture. A Vitis design requires a platform and applications. Platforms handle all hardware and system-related settings. They have two basic types: data center platforms and embedded platforms. Data center platforms work as an accelerator for x86 CPU hosts. Host talks to the data center platforms through a PCIe interface. Typical Alveo platforms like U200 are this type. When the data center platform includes an ARM processor, and the developer can use this processor, it's called data center hybrid platform. Currently, this type of platform is not public yet. Embedded platforms can work by themselves. They don't need external host processors. When the design needs acceleration kernels on PL or AI engine, the platform needs to be an embedded acceleration platform, or we can call it extensible embedded platform. When the PL and the PS are designed separately by hardware and software engineers, embedded software development platforms would be good. It doesn't support acceleration kernels on PL or AI engine, but only works for software development. The platform creation is simpler than extensible platforms. The traditional Vivado and SDK design flow is this type. Since the embedded use cases can be varied for each application, embedded platforms are fully customizable. Today we will focus on the embedded acceleration use cases. In all acceleration use cases, platform provides the hardware interface to application developers. It encapsulates the various hardware interface into logical interfaces. Platforms also provide various functions to application developers. For example, they would provide at least one memory controller. Sometimes, platforms can also provide board management features and security features. On the software side, embedded platforms provide a complete set of operating system and runtime libraries so that the system can boot properly and the acceleration applications can use the platform hardware functions. The application developers only need to focus on creating host applications and acceleration kernels. If we map the concepts to files, the hardware platform is a special Vivado design with all the IP functions and special metadata properties. The hardware platform is archived as an XSA file. The software platform should contain one Linux domain. The Linux domain should not only define the Linux components, such as kernel images, root file system, device tree, but also how this Linux can boot properly. So the BIF for boot image description and all components required by BIF, such as FSBL, PMU firmware, U-boot, and device tree, are needed. Sysroot is usually provided for host application cross-compiling. It provides the libraries for the host applications. Based on this platform, users can develop acceleration kernels and link them with platform hardware, then generate one XCL bin file. Cross-compile host applications with Sysroot to Linux ELF and package the executable with Linux images and boot the components into the final SD card image. After Linux boots up, the user can execute the host application to load the XCL bin and run the acceleration algorithms. In Vitis, there are two ways to organize software components. Kernel, root file system, and sysroot are usually large in space. They can take tens to hundreds of megabytes. When creating a platform, we can package these components into platform or defer the info to application creation time. Vitis allows users to use external software components because it makes the design flexible. When the software components need an update, leaving software components outside of platform package could skip packaging the platform again. At the same time, it also allows multiple platforms to share one set of software component. So Xilinx pre-built platforms deliver components separately. A frequently asked question is, it sounds great for this platform and application architecture, but if I need to make my platform every time, does the design flow seem more complicated than simplified? The answer is yes and no. It will indeed take more time if every design starts from creating a platform, but in most cases, a design can start from Xilinx pre-built platform. The design development procedure can usually be divided into several steps. First, we evaluate the key features that our design intends to use. If a Vitis library provides the feature, we can access it on base platforms. If we need to build any custom kernels, we can link them with the pre-built base platforms. Only when the platform needs more advanced interfaces, we can customize the platform. If the evaluation shows that the function and performance of these key features can meet the expectation, we can migrate the evaluation platform to final production hardware. Otherwise, we can stop early and find other solutions. In traditional design flow, you need to spend some time setting up the evaluation environment first. With Vitis, it gives you a shortcut to evaluate the key features first on Xilinx demo board or with Vitis emulation when the hardware is not available. Since using a pre-built base platform can save your time, let's learn how to use a pre-built base platform. Xilinx hosts the pre-built platforms on Xilinx Download Center. First, you need to download the platforms to your development server. Go to Vitis Embedded Platform tab. You will see the base platforms for different boards and architectures. If a platform is called a base platform, it's a static platform. For static platforms, the hardware link result contains the full bit configuration. During system boot, this full bit is loaded. When the host application executes the Excel bin file, it only reads the metadata from the Excel bin. Another type, the DFX platform, can dynamically load kernel PL configuration during runtime. When the system boots, only platform hardware is loaded. When the host application downloads the Excel bin file, it runs partial reconfiguration for the kernel hardware and reads the metadata from Excel bin. Most of the embedded acceleration designs use static platforms. If you remember, Xilinx delivers software components separately from the platforms. This common image contains Linux domain components like Linux kernel, root file system, sysroot, and boot components like PMU firmware and U-boot. To install the platforms, you just need to extract the packages to Vitis recognizable passes. Vitis can recognize platforms in these 3 platform search passes. You can extract software components to any pass. Provide the passes to Vitis when creating applications. When creating Vitis applications, Vitis IDE can list the platforms in the search passes. It also allows you to add more platforms when creating the application. When selecting the domain, it asks for the software component location. If you are using command line mode, you can pass the platform name and sysroot to V++. The platform usage flow is same for pre-built platforms and customized platforms. The target for the Xilinx pre-built platform is to provide the minimal essential features but leave the maximum programmability to Vitis users. To make software easy to use and extensible, Xilinx provides a package feed so that users can install additional software packages on the fly. Thus, even if the root file system in a common image doesn't provide your required software packages, you can install them with the DNF package manager. PetaLinux package feed provides all software packages supported by PetaLinux. Please refer to UG 3093 for the detailed usage steps. Now you've got all the context and we can dive into the platform creation steps. Since the platform creation has a lot of details, but our time is limited, I'll focus on high-level steps and important rules. Please refer to the tutorial for the step-by-step guidance and the more detailed explanation. From a high-level point of view, creating a custom platform is to prepare the components we mentioned before in platform architecture. Most of the components can be provided by the base bootable design. When creating a platform, the tasks are mainly to update the components for Vitis requirements. Finally, we validate the platform before delivering it to application developers. A base bootable design with Vivado and PetaLinux image can boot the hardware to Linux OS could give platform creation a good start. Board booting up is a time-consuming job for new hardware design. It needs to be done no matter with or without Vitis flow. It's important to make sure your base bootable design is correct before going forward because it could give you a clue to isolate the root cause if the generated platform encounter any issues. Peripherals on hardware should be tested by this base bootable design. Once the base design can boot properly, we can start update hardware for platform requirements. To make the hardware design comply with the Vitis platform requirements, we need to check whether it can provide these signals. One clock and its associated reset signals are mandatory. One clock can be the default clock. You can add more clock and reset pairs for better flexibility. Axis interfaces can provide the control channel and data channel between the kernels and platform resources. Usually, we will provide an XC master to control kernel start and stop. Kernels need to access memory. Memory controllers are instantiated in embedded platforms. So the platform needs to export the XC slave interface so that kernels can use the memory. XC stream interfaces are good for streaming data like audio, video, AD, and DA. It doesn't have the address info like memory mapped XC. For example, MIPI IP core generates XC stream. HDMI reads in XC stream. For video processing platforms, we should export these XC stream interfaces for kernels to process. If interrupt is not available, XRT will run in polling mode. In general, interrupt is recommended because interrupt mode would allow processors to work on other tasks instead of checking kernel status regularly. The hardware update will be done in Vivado. Before doing any setups, make sure to set your project as an extensible Vitis platform. If it's not created this way, you can update in project settings. Vivado has a platform setup tab if the project is an extensible platform project. Set up the XC port, clock, and interrupt information according to the wizard guidance. The platform setup wizard provides DRC to report issues in early stage. A common platform block design looks like this. It has a PS block for ARM processors, PS peripherals, and XC interfaces. It uses a clock wizard and processor system reset block to generate clock and reset signals. The interrupt controller can support 32 kernels. The INTR signal is left floating. Vitis will connect the kernels to the available clock, reset, XC, and interrupt during the linking stage. Versal design has similar requirements. The new blocks like XC knock and AI engine makes the block design look more complex, but the rules are the same: clock, reset, XC, and interrupt. To help users to start quick for Versal platform design, Vivado provides a user configurable example design template. I will demonstrate this later. Vivado exports the XC stream interface of AI engine automatically. User kernel can connect XC stream interfaces to AI engine. XC interfaces for memory access are provided by NOC. The control interfaces and interrupt connection are the same as MPSoC. After configuring the platform setup, export the platform with Export Platform Wizard. The generated XSA file would be used in the following up software setup. Step 2. Update software environment for platform requirements. Linux is required because the acceleration kernels need to be controlled by XRT, which currently only supports Linux on ARM. If you already have a working Linux environment from the base bootable design, you need to update the software environment to enable XRT. The XRT packages and its dependencies, including Zoco driver, need to be installed in the root file system. If you need native host application compilation on ARM, please install the XRT-dev package. Zoco driver requires a corresponding device tree node to describe the connection relationship of interrupt signals. There are no special requirements for the Linux kernel. The requirements look complicated, but since Petalinux does a good job of automation, the actual user manual work is minimal. Through Petalinux config for root file system, you can add XRT package. The common image we mentioned for pre-built platforms can be used for custom platforms as well. The device tree generator can generate XRT required device tree nodes if the XSA is an extensible platform project. Petalinux detects XSA type automatically. If you are using the common image, you can use XSCT or Vitis IDE to launch device tree generator. Step 3. Generate the Vitis platform. After we created the hardware, XSA, and software components, we can link them together and create the Vitis platform. Since BIF and boot component directory paths will be provided to Vitis to generate the platform, we usually copy all the boot-related files into one boot directory. uboot.src generated by Petalinux will be needed to be placed to a FAT32 partition on SD card, so we copy it to another directory. Linux components are optional to platform because they can be added during system project creation. Vitis 2021.1 can generate a default BIF file. User only needs to customize the BIF file when there are more requirements of the boot flow. We can create a Vitis platform in Vitis IDE by creating a new platform project. Provided the hardware XSA, create a Linux domain, set up the required fields of the Linux domain, generate the platform by clicking the build icon. The generated platform is in the export directory. We can also create a script and use XSCT to run this flow for automation. Step 4. Verify the platform. The platform creator should verify the platform before delivering it to application developers. We can check the platform metadata with the platform info utility. If the platform has memory map X interfaces, we can use a simple kernel such as vector addition to create a Vitis design, link the kernel to the platform to verify the basic platform features such as clock, XC for control, XC for memory map, and interrupt. If the platform has other special interfaces, platform developers should prepare other test cases. Platform developers can also enable emulation for the platform and running emulation before delivering the platform. We will introduce this advanced topic in the future. That's all for the Vitis platform creation methodology. In summary, the Vitis platform can help developers to start design earlier and easier. It increases the design portability and enriches the ecosystem. The platform creation process has been simplified in Vitis 2021.1 with several ease-of-use enhancements. Vivado customizable example Versal platform design can take you to a quick start of Versal platforms. Platform Setup Wizard in Vivado helps you set up platform properties and prevent errors. Device Tree Generator sets up a device tree for extensible platform automatically. Xilinx will continue to improve the ease of use of Vitis platforms. This is also a benefit of platform. With the explanations above, you should be able to understand my demonstration of a Versal platform creation. Now here is my demonstration of a Vitis platform creation flow. Create a directory. Launch Vivado. Install Versal Extensible Embedded Platform example. Create a new example project. Set up project name. Select target board. Configure your example project with clock settings, interrupt settings, and memory settings. Wait for a while, Vivado will create an example project. In the created block design, you can see a Versal processing system block, 2 XE NOC blocks, an AI engine block, some smart connect blocks, and an interrupt controller. DDR controller is in the NOC DDR block. You can see this is an extensible Vitis platform project. Launch Vitis Platform Setup tab. Access slave ports of NOC DDR4 are enabled. Access master interfaces from Smart Connect are enabled. The total number is 32. 3 clocks from Clock Wizard. The output clock will be phase aligned. 32 interrupt signals. We need to generate block design before export the platform. Launch Export Hardware Platform Wizard. You can select platform type. I wish to use this design for both hardware and emulation, so I select hardware and hardware emulation. The XSA file is generated. Prepare software components. Source Petalinux environment. Create a Petalinux project with the XSA file we exported. Petalinux reports an error because the CentOS 7.8 here has a GCC 4.8, but Petalinux requires higher version. Enable Yocto Build Tools extended option to work around this requirement. Now let's enable XRT package. This is the only menu task requirement for extensible embedded platform. Use a pre-built device tree for VCK190 board. Set the root file system type to be ext4. Build Petalinux. It takes about 25 minutes on my server. Check the generated image files. Take a look at the auto-generated device tree file for Zoco. It tells Zoco driver how to interact with interrupt controller when a kernel generates an interrupt signal. It also sets the interrupt controller input number to 32. Build Petalinux SDK. It takes about 8 minutes on my server. It generates sdk.sh file. Now let's prepare the software components into one directory for Vitis platform creation. Create a boot directory for boot components. Create a FAT32 directory for SD card. Create a sysroot directory to install sysroot. Copy boot components from Linux image directory to boot directory. Install sysroot. Create a Vitis workspace and launch Vitis. Create a platform project. Add XSA file. Create Linux domain. Add Linux domain info. Generate BIF file. Leave rootfs and sysroot info empty. Build the platform. You can see the generated Vitis platform is in the export directory. We should also verify this platform. Create a vector addition application with this platform. Prepare root file system and Linux kernel image. Build the application for software emulation. Launch software emulation. Here is the result. We should do the same verification flow on hardware emulation and hardware. If you need more information, please refer to these documents. I highly recommend you follow the tutorial and make your own platform. Thank you for watching.